All right, here we go. Okay, so we're going to wrap everything up here with a discussion of Newton's second law and actually explore how this all ties together and describes how things move after we find out what caused them to move. But a quick reminder back into the first lesson, we had a definition of acceleration. In particular, our average acceleration, mind you, that's an A with a straight line over it, not an arrow. And our acceleration equals our change in velocity, and that's got an arrow over it, divided by our change in time. Okay, because we know that acceleration, but this is our total change in velocity, not necessarily an instantaneous moment. It's just if we, so let's say we go, 25, we have an increase of 25 meters per second. And this occurs over the course of 10 seconds. This is going to equal 2.5 meters per second, right? That's our total. When this 25 meters per second every second is going to simplify to 2.5 meters per second squared, and that's how we get that squared in the acceleration units. That'll be a positive value. So our velocity will change at a rate of 2.5 meters per second every second. Yeah? Thumbs up on that part? Okay. Where this really comes into play is in our Newton's second law, where we had Newton's first law was if objects are in motion, they stay in motion. If objects are at rest, they stay at rest. If there's no force acting on it, right? So that was, the first one was if sum of the forces equals 0, then our acceleration equals 0, right? It will not change. Our velocity won't change. We won't have a change in motion if we don't have a net force. Well, Newton's second law is if our net force does not equal 0, then our net force, some of our forces, our net force, will equal the mass of the object times the acceleration of the object. Okay, and this is the most important equation in all of physics, in all of classical physics. F equals ma. Just about everything can come from that. All right. So the problem that we're going to do first is a real basic one. If we have a 1.5 kilogram ball and an acceleration of 9 meters per second to the left, what is the net force acting on the ball? Well, we identify our stuff. We've got a mass of 1.5 kilograms. We have an acceleration of 9.0 meters per second to the left. This is the vector part, right? We have the magnitude and the direction. So what is our force? Well, if we use Newton's second law, Newton's second law is the sum of our forces. Our net force equals our mass times acceleration. Because there is only one force, we're just looking for the net force. Okay, that's what our F equals. Okay, our F is going to equal, I pause for a sec. Have you guys recognized that when we have bold letters, those are vectors? And when they're not bold, they're not vectors? Okay. If you haven't recognized that's the case. So when that one, those are talking about vectors. Right here, that's not bold, right? It's just talking about the magnitude in that case. Right? That's just doing the math of it. Right? But then it comes back to bold because we add the to the left. So our force is going to equal our mass, which is 1.5 kilograms. And our acceleration, right, to sub in the A, 9.0 meters per second squared. That really equals 13.5 newtons, but we only have two significant digits. That's going to round to 14. So that's going to be 14 newtons, and then we add the to the left in there because that's the same direction as the acceleration. Net force and acceleration are always in the same direction. I apologize for my messy handwriting. I have a very sensitive stylus that doesn't always recognize when it's not touching something. All right. Right, so the sum of our forces and our acceleration are always in the same direction. Right, which kind of makes sense, that if we have a net force, we will accelerate. Therefore, they have to be going in the same direction. All right, so we are going to start with our first example here. Okay, David Purley, a racing driver, survived deceleration. I hate this term. This really just means negative acceleration. From 173 kilometers per hour to 0 kilometers per hour over a distance of 0.66 meters. Holy moly. When his car crashed. Assume that Purley's mass is 70.0 kilograms. What is the average force acting on him during the crash? All right, so average force, Average force, does his mass, we know that F equals ma, right? Does his mass change?
Nope.
I mean, he may have evacuated himself when he realized he was going to crash that hard, but no, his mass doesn't really change, right? So if we're talking average force, wouldn't that just be mass times his average acceleration? Does that make sense? Because their mass doesn't change, so the only things that are changing are the force and the acceleration. All right, so what do we need to find? We need to find, we're looking for the force. Force equals, don't know. We have a mass equal to 70.0 kilograms. And we have an acceleration, which we don't really know, but we can figure it out, right? Yeah? Okay, so our average acceleration is going to equal oh wow, we just have a distance. So we have two velocities and a distance. Okay, how are we going to do this? We have two velocities and a distance. You guys remember how to do this one?
No.
Okay, so we go back, we set the Wayback Machine, and we remember that we have an equation that says velocity final squared equals velocity initial squared plus 2 times our acceleration times our distance. It's in there. Go back and look at lesson 1. Okay, velocity final equals 0. Velocity initial, (173 kilometers per hour). We're going to square that. And that is equal, and that we add to that 2 times our acceleration times our change in distance, which was 0.66. 0.660 meters. Okay, we have a bit of a problem here, though. Kilometers per hour, we need to convert this to something that we can manipulate. We need to convert this to meters per second. So, 173 kilometers per hour, where we have 3,600, oh, sorry, wrong side, where 1 hour is 3,600 seconds, right? 60 minutes in an hour, 60 seconds in a minute, 3,600. We're good. Okay. And 1 kilometer is 1,000 meters. Okay. And this will give us hour, kilometer, that will give us meters per second. So our 1,000 and our 3,600, that can cancel, so we can just divide by 173 divided by 3.6. Okay, you will eventually realize that kilometers to hour to meters per second, you divide by 3.6. It's just the It'll always work that way. And that is going to equal, I'm not going to do this on screen, 173 divided by 3.6 is 48 meters per second. So now all of a sudden, over here, we have 48.0 meters per second quantity squared plus 2 times A times 0.66 meters. And now we have units that we can work with. And I'm going to skip a little bit of the math here. A is going to equal 48.0 squared over 2 times 0.660. And that gives us an average acceleration. Or sorry, there's a negative in there. That should be negative of all of that. Negative 1,700 or 1.71 times 10 to the third meters per second squared. That's our acceleration. Would you like me to write that number again? Okay. That is negative 1.71 times 10 to the third meters per second squared. So what's our average force? Well, our force equals mass times acceleration. Our average force equals our mass times our average acceleration. So our force is going to equal 70.0 kilograms times a negative 1.71 times 10 to the third meters per second squared. And that gives us 1.22 times 10 to the fifth newtons. Oh, it didn't take. Okay. So that's the answer to the first one. What is the average force acting on the crash? So we identified this question here. Okay. Then compare this to Pearlie's weight. Right? So Pearlie's weight is 70 kilograms. Okay. Equals 70 kilograms times force of gravity. I'm just going to call it 10 right now. All right, so his weight equals 700 newtons. So 1.22 times 10 to the fifth newtons divided by 700 newtons. Okay, so the force to weight ratio is 175. In other words, he pulled 175 G's during that crash. This is how we compare the force. We find the ratio. And he pulled 175 G's during that. Okay? So that's how we do one of these problems. Okay, we identify our given. Okay, we identify what's being asked. Okay, and we look for hints. Okay, and we start plugging stuff in. Okay, there are many, many variations of these kinds. Okay, I would like to do another one to give you guys a little bit more example. So we'll do number 2 on the practice set. Because this one is a little different, because they're all a little different. They're all separate. They're all different from each other. So number 2, a giant crane in Washington, D.C. was tested by lifting a 2.32 times 10 to the 6 kilogram load. That is a whole lot. Find the magnitude of the force needed to lift the load with a net acceleration of 0 meters per second. All right. This means what?
He's not accelerating.
What's that?
He's not accelerating.
He's not accelerating, which means the total forces acting on it is 0. All right. So we still need to draw, okay, a crate, because that's what we do. And on this crate, we are lifting with 2.3232 times 10 to the 6th. Oh, no, I lied. We'll just call this our upward force. But if it's by a cable, it's a tension. And then the whole reason the tension is there is to get it off the ground, and so it's fighting with gravity. All right, do we have any forces left or right? No, we don't. So the sum of our forces in the x direction equals 0. The sum of our forces in the y direction equals tension plus mg. And those also equal 0 because we are not accelerating. In other words, just saying that our tension is equal to gravity. All right, that's going to be our tension. So let's find out how much this thing actually weighs. Well, this is, okay, so our tension is going to equal this times gravity. I'm going to use 10 again, equals mg, negative mg. Okay, which is going to equal a negative times 2.232 times 10 to the 6th kilograms times negative 9.8. Oh, no, sorry, I'm going to use 10. Times the negative 10.0 meters per second squared. This is going to give us 2.232 times 10 to the 7th. Because if you multiply by 10, you get to increase the exponent of your scientific notation, right? All right, so that is our tension. Our tension equals 2.232 times 10 to the 7th newtons. That brings us, so we'll box that bad boy in. So that's the tension. That is the magnitude of the force needed to lift the load with a net acceleration. All right. B, if the same force is applied to pull a load up a smooth slope that makes a 30-degree angle with the horizontal, what would be the acceleration? So we need a 30-degree slope. For our crate. Oh. We need a 30-degree slope for our crate. That's an ugly looking crate, but that'll do. It's been banged up a bit. It was delivered by FedEx rather than UPS. All right, so we've got a tension. That was just a joke. No offense to anybody who's related to FedEx people. All right, so we have a tension that's pulling up the slope. Okay, this is where our free body diagram comes into play. What other forces do we have?
Gravity.
We have gravity. And we have another one. When we mention a smooth slope, okay, it's just code. It means that it's not that it's frictionless. That it's to be ignored. Okay, but there is another one. I'll give you a hint. It's going to go in that direction. You got it, Charlie?
Nope.
Is it?
Normal force?
Yeah, was it?
Normal force.
Yeah, normal force.
Oh.
It's sitting on a slope, right? It has a normal force. Remember, it doesn't. The normal force is just perpendicular to whatever surface it's contacted with. So if we're at an angle, we have a normal force. All right. In fact, I'm gonna pretty up my. Oh, it's down here. Let me pretty up my gravity here. There we go. Okay. Okay, now we have some other stuff, and this is going to take. Yeah, we can do it. Okay. Actually, I want to pretty up the tension too. Okay. So now we need to get in. We're going to take our axes to be along, so this normal force is going to be in the y-axis, and our tension is going to be along the x-axis. Right? So the whole thing's kind of rotated. Follow me there? All right. So that means our gravity has two parts to it. There we go. Our gravity has two parts to it. It's got that. No. And it has that part. Okay, so we learned this when we were resolving vectors. Okay, in lesson 1. All right, so now we have these two parts of gravity. And what's this angle right here, guys?
Seems like a right angle.
No, this one's the right angle over here.
Oh, wait, hold on.
That's our right angle. What's this one right here?
30.
What's that?
30.
It is 30 degrees, right? Okay, and the way to tell that that's 30 is if it's with the normal force, right? It's going to go through the same amount. If you go through an incline, your normal force will tilt through the same degree as the incline of the slope, right? So this change from straight up and down to going this way by a amount of 30 degrees. Okay, so, and we're going to go through this part kind of quick. This part over here is now mg cosine 30 because it's next to the 30, right? Adjacent hypotenuse, so we know that's the cosine. And this guy over here is mg sine 30 because it's opposite the 30. Okay, are we cool on that conversion? Getting that right off. All right. So now we need to do our Newton's laws equations because we have all of our forces lined up in our x and y directions. So we have the sum of our forces in the x direction. Here's our tension, right? We have tension plus this guy down here, mg sine 30. And then we have the other one, which are the sum of the forces in the y direction, which is our normal force, plus mg cosine 30 degrees. What can you guys tell me about the normal force and about our forces in the y direction? Is this thing accelerating off the slope or accelerating into the slope? No. So that means this one's going to be 0, right? Okay, so we can tell right now that the normal force is going to equal mg cosine 30. That is the normal force. Okay, so normal force equals, and we found that mg, right? We found that over here was the 2.32. So 2.232 times 10 to the 7th newtons. Okay, and cosine 30 is root 3 over 2, which is 0.866. And we can figure that. So one of you guys can figure that out. The sum of the forces in the x direction, however, is a little different. Okay, this may actually be accelerating up the slope, right? In fact, we need to find that. What would be the acceleration up the slope? All right. So we know that the sum of our forces then is going to equal mass times acceleration. So our tension, we found that for E4, it's this 2.232 times 10 to the 7th newtons plus a negative 2.232 times 10 to the 7th newtons times sine 30, which is actually 0.5. And all that is going to equal mass times acceleration. Well, look at that. We have our tension, but since our tension equals mg, this is half of our, this is over here is going to be half our tension, so it's really just going to be half of this. So mass times acceleration is going to equal 1.116. Hopefully you guys can see that. Times 10 to the 7th newtons. Right, because if we subtract, if it's 1 minus 0.5, right, it's going to be 0.5 of x minus 0.5x is going to equal 0.5x. Right, so this is going to wind up being half of our tension. But our acceleration, our mass over here is this 2.32, right? So we have our acceleration is going to equal 1.116 times 10 to the 7th newtons over 2.232 times 10 to the 6th kilograms. We know that this was times 10 divided by 5, or divided by 2, right, of our original mass, right, it was mass times 10, and then divided by 2. So our acceleration is going to equal 5 meters per second squared. Okay, that's just me doing some math tricks. Go ahead and fill this into your calculator if you want. Okay, so that is the magnitude of the acceleration. So the acceleration really would be, all right, A equals 5 meters per second up the slope, because we had some kind of direction. And that is number 2. And that's where we're going to finish it. Examine these. These sum of the forces X, sum of the forces Y. That is crucial to doing these. You have to separate them into their X's and Y's in order to be successful with these. Once you've done that, and once you practice these, you'll get them. It takes a little bit of arithmetic work, but you guys can get this.